Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, good afternoon, everyone, or good day, good morning, depends on where you are in the world. And today we have a new event of the AI for Good, which is specifically part of the series that is related to the geospatial world. And today we have a very, very super interesting presentation, a super interesting speech given by a very talented professor, very young and talented professor. So I'm very happy today to have here with us Professor Begum Demir. Begum is a professor and founder head of the Remote Sensing Image Analysis Group at the Faculty of Electrical Engineering and Computer Science at the Technical University of Berlin. And she's the head of the Big Data Analytics for Earth Observation Research Group at the Berlin Institute for the Foundations of Learning and Data. She performs research in the field of processing and analysis of large-scale Earth observation data acquired by airborne and satellite-borne systems. But she was also awarded by the prestigious 2018 Early Career Award by the IEEE Geoscience Remote Sensing Society for her research contributions in machine learning for information retrieval in remote sensing. And then in 2018, again, she received a starting grant from the European Research Council, the ERC, for her project, Big Earth, Accurate and Scalable Processing of Big Data in Earth Observation. And then she's also an IEEE senior member and Alice Fellow. So I'm very happy to have here Begum today with us, and she will tell us about Deep Earth Query, information discovery from Big Earth Observation Data Archives. So Begum, very, very welcome. And as I already said you before, I'm looking forward to learning something for your lesson. So I'm very excited to have you here. Thank you for accepting of being with us. And now the floor is yours, Begum.
Thank you very much, Professor Brovelli. It is a great pleasure for me to present our research activities on information discovery from Big Earth Observation Data Archives. And also thank you very much for the very nice introduction. So now let me share my slides. Okay, so I hope everybody can see that.
Yes, yes.
Okay, great. So today I will be talking on Deep Earth Query. That is all about our methodologies, algorithms developed for information discovery from Big Earth Observation Data Archives. As it was mentioned, this work is supported by European Research Council through the Big Earth project. And I'm currently leading two different research groups in Berlin. One of them is RSIM at Faculty of Electrical Engineering and Computer Science of TU Berlin. And the other one is Big Data Analytics for Earth Observation. So in short, Big Earth. So it took the name of our ERC project. That is at BIFOLD. So BIFOLD stands for Berlin Institute for the Foundations of Learning and Data. So actually it is a national AI competence center in Berlin that aims to make important contributions to the development and applications of artificial intelligence. So at Bifold, we research on theoretical and algorithmic foundations of data management and machine learning, as well as related technologies and the systems. At my team, we are developing AI models for different Earth observation problems. Okay, so and also just to note that Bifold is currently supported by the federal government and the state of Berlin as a national AI competence center. Yeah. So as I mentioned, today's topics is on information discovery from the big data archives for Earth observation. It is very important because as a result of advances in satellite technologies, the amount of data in our data archives for Earth observation is significantly growing, not only in volume, but also in diversity, and it carries important information about the state of our planet. So as an example, the volume of ESA's Sentinel's archive is currently almost 20 petabytes, and per day we have more than 10 terabytes of Sentinel data acquired. So when I talk information discovery, in today's talk, I will be mainly focusing on query by example. So how we can discover information from big data archives by querying through an example. So let me show you an example. Okay, so here you see a query image. That's a Sentinel-2 image acquired after a very big forest fire in southern part of France. And you know, analyzing burnt forest areas is important for climate change and ecological studies. And finding all the burnt forest areas all around the world is currently feasible, right? Of course, some of the forest fires we know because we hear about them, but there are many others we don't know because there is no access. However, all this information is hidden in satellite data archives, and we can extract this information by developing systems that have the capability of query by example. So this term of query by example is common in space agencies, space companies, but from the researcher's point of view, it is also called as content-based image retrieval. So we have an image that is called as a query image, and we would like to retrieve the images semantically similar to that. Okay, here in this case, it is the burnt forest. So query can be also defined by a pair of images to model, index, and search change areas. Okay, so here, for example, we see a deforested area as a query data. And then a query by example system here is aiming to retrieve other deforested areas all around the world. So if we have a database, so-called archive of global scale data, of course that is possible to find, retrieve, search such data. So in general, query by example systems contain two main blocks. Okay, so the first block aims to characterize the content of query data and those of archive images. Okay, so then this is for Earth observation description. Okay, so it is aiming to describe the semantic content of satellite data, both in the archive and in the query. And then the second step is for search and retrieval. So the aim is to match the features of the query to those of archive images and return to the user the most similar ones. Okay, so of course, given the size of the archives that we are currently handling, it is very important to have that search in a scalable manner in addition to accuracy. Okay. Okay, so in today's talk, I will be focusing on how to describe the content of satellite data in an accurate and scalable manner to allow image search and retrieval for different Earth observation problems. Okay. So we can really group the existing systems as traditional and advanced systems, recent systems, let's say. So the traditional systems, they separately optimize feature learning and image retrieval. Okay, so for example, to represent the content of images, both in the query and in the archive, one can use traditional feature extraction methods, like, for example, histogram-based features can be used here, or NDVI can be used here, and so on. And after extracting the features, which we also call as handcrafted features because they should be defined before any retrieval stage, then the retrieval can be done by using different approaches. For example, one can simply use k-nearest neighbor algorithm here because you need to match the feature of the query to those of the archive images, and then you can rank the similarities and return to the user the most similar ones, okay? However, as you can imagine, if you have petabytes of data to scan, to apply in KNN, this can be very time demanding, of course, depending on the length of the features to represent the images, but also their characteristics, right? It cannot be very feasible to apply in a scalable manner, this approach. So that's why there are algorithms called as hashing to represent the content of images with binary codes to handle the scalability issues. I will come back to that very soon. So recent systems, unlike the traditional systems, they aim to jointly optimize feature learning and image retrieval. So there you don't need to define handcrafted features, but you let the model learning the features to minimize the retrieval error. So to maximize retrieval accuracy, okay? So there we have deep neural network based models to define an image retrieval problem. Okay, so today I will be mainly talking on recent systems. Okay, but if you are interested in also understanding how the traditional systems are working, I would like to refer you to the papers that you can see here. Okay. Okay, so as I mentioned, if we would like to achieve scalable search and retrieval, we need to represent the image content in such a way that search can be done in a scalable manner. Okay, so the solution that is very common in these years is based on hashing. So hashing aims to model the content of images both in the query and in the archives with a binary code. Okay, so if we represent the images with binary code, then the image retrieval can be done by using just Hamming distance, simple bitwise operations, by using simple bitwise operations. But also we can just index our images in the archive in a hash table where different hash buckets are related to a specific hash code. And then image retrieval can be done by simply retrieving all the images in the same hash bucket with the query. Okay, so this is an example of a hash table. You see hash buckets and the hash codes for 2 bits representations, just for the simplicity. And then if I have a query image that has a hash code of 00, I can just retrieve everything. So all these 3 images in this hash bucket having the same hash code with the query, okay? This allows me to achieve scalable image search and retrieval. So, of course, the question here is how we can represent the image content with a binary code. Okay, there are several different approaches presented in the literature. It's not only in remote sensing, but also in machine learning communities. It is an important topic, and there are several different hashing approaches like graph-based hashing, unsupervised hashing, multimodal hashing, adversarial hashing, and so on. And actually, traditional methods were mainly based on kernel-based hashing and so on. Recently, we see that deep learning-based hashing algorithms provide much better performance and accuracy than traditional hashing approaches. Okay. So now I would like to mention you one of our earliest deep learning-based hashing methods. So it was in 2018, we developed a metric learning-based deep hashing work. We call it as Milan. And that model actually considers a pre-trained model that is InceptionNet, but it can be any other pre-trained model. So then we just have a small model with 3 fully connected layers. And then it's very important how we are defining the loss functions here. So we have 3 different loss functions. One is triplet loss. This is for learning the metric space. And the other one is representation loss. This is for pushing the activations of the last layer of the network to be binary. And then there is bit balancing loss. Bit balancing loss encourages the network to produce hash codes having an equivalent number of zeros and ones. Okay, so this representation loss and bit balancing loss are for binarization, and triplet loss is for the metric space learning. So as I mentioned, we have the pre-trained inception net, and our remote sensing images are given as input to this model. And then the output features are given as input to the Milan. And Milan, based on the joint use of these three different loss functions, produces binary hash codes. So whenever you have a binary hash code for each image, you can apply search and retrieval by using, as I mentioned, Hamming distance base ranking or just a hash table approach. Okay, so so let me tell you a little bit more about what is triplet-based deep metric learning. So that is very important because while we are designing image search and retrieval system, we are interested in characterizing the images based on their similarities, right? Because image retrieval means searching and retrieving semantically similar images to the query. So we want to define image content in such a way that similar images will have similar feature vectors and vice versa. And then triplet loss helps us to achieve this goal. So it aims to define a metric space where similar images have similar descriptors and these similar images have dissimilar descriptors. Okay, to do that, it needs to define a triplet. So triplets contains an anchor, okay, and a positive image to the anchor and negative image to the anchor. Okay. So if you have images or image patches with single label, so annotated by single label, like you can see some examples on the right side, like there is a patch and the label is airplane, or there's a patch, the label is storage tanks. So positive image means an image that shares the same label with the anchor, and negative image means an image that doesn't share the same label with the anchor. Okay, so that is the training set. So that is different with respect to classical training sets used in land-use land-cover maps generation problems. So then triplet loss learns that metric space to define the features close to each other for positive and anchor, and dissimilar features for negative and anchor. Okay, and then as I mentioned, the other two loss functions, like the representation penalty loss, so-called also the push loss, and bit balancing loss are for the binarization problems. Okay, so we have used simply these three loss functions to generate the binary codes to represent the images and apply it to the aerial data set that we had at that time, okay, in 2018. And we see that by using deep hashing, we can obtain better retrieval results than kernel-based hashing, which was very popular before deep learning entered to our life. So here, for example, the query on the right side, you see the results. That is a query that includes an airplane. And then second row is showing the retrieved images if a kernel-based hashing is applied. And the third row is showing the images if Milan is applied. So as we see, Milan can return to the user semantically more similar images. So actually here there are two issues that I would like to highlight. So that model, Milan, although we confirm that the combination of three loss functions are convenient for hashing problems, it takes a pre-trained model on ImageNet. ImageNet has characteristics significantly different than, for example, Sentinel-2 images, right? And if we are just using aerial data, it is less critical. But if you would like to use multispectral images like Sentinel-2 images, this would create a limitation. So on the other side, it's very difficult to have pre-trained models trained on large-scale remote sensing data. So that was our concern problem while we were designing this model. But since we applied it to the aerial images, we were feeling okay with the results. But then we immediately started developing a new data set that time. And so actually that paved the way for BigEarthNet. So maybe you may not hear about BigEarthNet so far, so I will be very shortly mentioning about it. So it's a large-scale benchmark archive that includes almost 600,000 Sentinel-1 and Sentinel-2 images acquired over 10 European countries. So we made publicly available not only the dataset itself, but also the pre-trained models on BigEarthNet images. And we think that it opens promising directions to advanced studies on the analysis of large-scale Earth observation data archives. So yeah, it has been downloaded more than 10,000 times since we released it. It is currently available at its own website, that is BigEarth.net. And also you can have access to it through Google Earth Engine and TensorFlow. And also it is at different ML hubs, okay? So since then, we started to use BigEarthNet in our experiments while designing search and retrieval systems. Okay. So BigEarthNet is different with respect to the other aerial dataset that I showed you some minutes ago. So we have 600,000 patches, Sentinel-2 and Sentinel-1, but these patches are annotated by multiple land-use land-cover labels, okay? So these labels are coming from the Korean land cover database of the year 2018. Okay, so you may have heard about this Korean database. This has been produced by the European Environment Information and Observation Network of the European Environmental Agency. So since the patches that we defined are annotated by multiple labels, we need to define models, machine learning models that can model multi-labels per image. So that led us developing multi-label image search and retrieval systems, okay? So here, there are images, image patches, and multiple labels assigned to that. And then the problem appears like multi-label image search and retrieval, okay? So then the question was, yes, triplet loss is working well to define a metric space, but how to define triplets if the images are annotated by multiple labels? Okay, because it was simple in the case of single labeled training images, but the challenge appears if the patches are multi-labeled. Okay, so then we developed a model, a retrieval model, that can select relevant hard and diverse triplets for multi-label remote sensing image retrieval problems. Okay, so this work has been recently published at the IEEE Transactions on Geoscience and Remote Sensing. So in today's talk, there is no time to really enter too much in technical details. I will do all my best. I will provide some details, but for the further details, I would like to always refer you to the related paper. So we have a batch of samples, a batch of image patches, let's say, with multiple labels. And our problem is how to select triplets from there by considering multiple labels of images. So first, we work on defining anchors, and we wanted to select anchors that are diverse to each other in the feature space so that they should be not redundant, because training already takes time, and we would like to define a small subset for the triplets so that we can also reduce the training complexity. So we wanted to select diverse anchors. So, and then for each anchor selected, we define a strategy to select relevant hard and diverse positive and negative samples. So very briefly, Yeah, diverse anchor selection is based on an iterative algorithm. You select one randomly and the other ones that are distant to already selected ones. Okay, so it's very simple. For the positive and negative samples, we first analyze the relevancy. So relevancy based on the class label similarity. So a positive image is relevant if the class label similarity is high, and a negative image is relevant if the class label similarity is low. Then we evaluated hardness based on the distance to the anchor. So if a positive image is hard, if in the feature space distance is high to the anchor, and a negative sample is hard if it is distant to the anchor is small. Okay. Then I will not go into the mathematical definitions here, but after selecting relevance and hard, positive and negative images, we want them also diverse from each other. So we don't want to add redundant positive images for a given anchor or redundant negative images for a given anchor. So then we use a similar approach as in the diverse anchor selection step, and then selected the diverse ones. So these help us to select anchors that are diverse and positive and negative images per each anchor that are relevant, hard, and diverse. Okay. So let me show you some results here. So if we just select these anchors, positive, negative images randomly, the performance, I mean, we measure the performance on 3 different metrics here, but let's focus on recall. So if we select positive, negative images and their anchors randomly, the recall is 73. And if we use our approach, it is 75. Of course, we set the parameters very carefully so that the comparison is fair. And then below, on the left below, you can see the retrieval results. So in A, you see a query image. Okay. In B, these are the retrieved images if we use a random selection approach. And below, you can see the images retrieved if we use our approach. Okay. So then we had a system, okay, that can apply search and retrieval by considering images with multiple labels on BigEarthNet. So at this point, we didn't need a pre-trained model on ImageNet anymore, for which we were really very happy. And then we developed a prototype search engine, okay? On the right, you see an image that is representing our BigEarthNet portal. So this portal allows us to select an array of interest to query, and then returns the images similar to that over BigEarthNet. That means over 10 European countries. So there's no time to show you the demo, but you can just scan the QR code here, and then you will be having access to our YouTube channel where we present the demo, okay? And actually, the demo will be also presented next September, coming September, at the International Conference on Very Large Databases, VLDB. Okay. So that is a prototype only, but we are very ambitious. We would like to have our algorithms operational on a real Copernicus data search and retrieval search engine sooner or later. Okay, so this is just the first step. Okay, so then given the time, I will be from now on moving quick, just aiming to give you a vision on what are the needs, recent trends, and recent works on image search and retrieval. Okay, so we recently observed that while representing the content of images, it is also important to model regions and region relations, okay? So then we develop a graph theoretic deep representation learning method, again for multi-label remote sensing image retrieval problems. And for the details, again, I refer you to this work. This was presented last year at IGARS. Okay, so it has two main steps actually. So first we describe the regions associated to classes present in the training image, and then our aim is for our training images to represent the graph representation. Okay, edges are defined based on the special relationships of classes because we would like to characterize the region relations. And then actually in the second step, where we aim to model multi-label co-occurrence relationship of any image in the archive, we develop a new loss function that is called as region representation learning loss function, and it allows to describe the content of images based on multi-label co-occurrence information because it automatically predicts the regional relationships of a given image. Okay, so and we have seen that modeling the regions and region relations can help us better characterize the complex semantic content of remote sensing images. And then we have seen with respect to a single use of triplet loss function, if you model the region relations, we can improve the performance more than 10%. Okay, this is a big improvement. However, there is one drawback here. So if you would like to describe the content of images with a graph, you need a pixel-based annotations. And if you are targeting global scale search and retrieval or large scale continental regional, also, it's very difficult to have a pixel-based class labels. So to address these problems, one can use thematic products, as in our case, we use Korean labels. But such labels can also contain noisy labels, and this can really distort the learning of the model. Okay, so that's why, although this is a cool approach, improving the performance with more than 10%, we need to be very careful. And currently, we are working on developing models that are robust to label noise. Okay. So, and then another approach we have recently developed is on multitask learning, because we have observed that defining different tasks to represent the content of images for retrieval problems is attracting attention, and it is beneficial to represent the complex content. And these different tasks can be image classification and so on. So, but the problem is the existing methods, they employ a joint optimization algorithm on the direct aggregation of the task-specific loss functions, which can lead to limited retrieval performance if tasks compute or even distract each other during training, and also when one of the tasks dominate the whole learning procedure. Okay, so to address all these issues, we define a novel approach that is called as plasticity stability preserving multitask learning. So our approach preserves the plasticity of each task and stability in between learning consecutive tasks for the whole learning procedure. And that is a theoretically appealing approach. So it is based on two different loss functions and a learning strategy. So I would like to refer you to this work. And if you have different tasks in your hand to learn together, not only for image retrieval problems, but also for other problems, you need to always consider this limitation that I mentioned. And maybe our approach that is defined in this work can also help you to address these problems in your applications. Okay. So another approach that we work at the moment is cross-model image retrieval. That aims to search and retrieve images from one modality to retrieve images from another modality. Okay, so you can consider it as query is a Sentinel-1 dataset, and you want to search and retrieve images from Sentinel-2 archives. Okay, at the moment this is possible, so it is also called as a cross-model retrieval, image to image, but images are from different modalities. Okay, so to address this problem, we develop a self-supervised approach actually that includes 3 different loss functions. One is to maximize the mutual information of different modalities for intermodal similarity preservation, because it is necessary. The intermodal similarity preservation is a must And then the other loss function is to minimize the angular distance of multimodal images for the elimination of intermodal discrepancy. And then the third loss function is to maximize the cosine similarity of the most similar images within each modality for intramodal similarity preservation. Okay, so joint use of these three different loss functions allow us to define a cross-model image retrieval system. Okay, so then actually this work has been recently accepted to be presented at the IEEE International Conference on Image Processing, ICIP, next October. Okay. So then another important research direction is to index the images while compressing them. We find it very interesting and very timely because nowadays, because of the size of the data archives, images are compressed, right? So then they are stored in compressed format. I'm talking about operational data archives, real data archives, not the benchmark ones. So then when you want to apply any type of analysis, you may need to decode these images. And if you want to apply search and retrieval, decoding huge amount of compressed data can be very time demanding already. So we wanted to design a system that can avoid this issue. So as a solution, we develop a framework that compresses the images while indexing the images. So image compression here in terms of the image storage size reduction, indexing is in terms of the hashing that I mentioned some minutes ago. So here for compression, we use a deep learning based compression algorithm that is based on autoencoders. And for the deep hashing, we use the loss functions for the binarization that I mentioned previously. So at this point, if you would like to apply search and retrieval, if you have already indexed your data in a hash table, you don't need to decode all the images before applying indexing. But after image search and retrieval, only the most similar images returned to the user can be decoded to visualize them. Okay, so this significantly reduces the computational time required for decoding. At the moment, there's also another very interesting research direction, which is how to analyze images in compressed domain, okay? So we see that deep learning-based compression algorithms are providing much better performance than traditional compression approaches. So for example, as you may know, Sentinel-2 images are JPEG 2000 compressed, but recently there are a couple of works that demonstrate that deep learning-based compression performances are much better than JPEG 2000, okay? So then deep learning-based compression models also allow us to process and analyze the data on compressed domain also directly. So this is a very interesting research direction for us at the moment, okay? And this work will be presented next week at IGAS. Okay, then another interesting research that we are at the moment conducting is again about cross-modal retrieval, but in this case, not image to image, but it is text to image. So the query so far in all the works that I showed you is represented as an image, right? So Sentinel-2 image to query Sentinel-2 archives, or Sentinel-2 image as a query to query the Sentinel-1 archives. But here the focus is if the query is a text. So text can be caption of an image or yeah, a textual description that characterizes the content of the images in a text. So and then how to retrieve images if the query is a text. So that led us to develop our unsupervised contrastive hashing model. Okay, so actually that is a model that that characterizes intramodal characteristics through different contrastive losses. And also for the binarization, we use the standard loss functions that I mentioned you before, like bit balance loss. Okay. So we have seen that that is a very important research direction, especially now considering that space agencies are interested in so-called AI assistant querying the databases by images or just image captions, okay? Okay. So yeah, this work is also very new. A couple of months ago, we have presented it at ICASP. Okay, so now, given that I have 4 minutes remaining, I would like to conclude my talk with giving some feature ideas. So considering that Earth observation data archives are growing, it is very important to develop search and retrieval systems that can be operational on not only at image level, but also at the textual data level, okay? And since Earth observation data archives are multimodal, it's also very important to develop multimodal search and retrieval systems. So we think that hashing-based methods that allow us to achieve scalable search and retrieval are very promising for retrieval problems in remote sensing. And they can let us obtaining fast and scalable search and retrieval results. So we are at the moment working on developing a retrieval system that can be operational at global scale. So as I mentioned, BigEarthNet includes 10 European countries, and so far we always tested our algorithms on 10 European countries. But we would like to go for global scale. And of course, at this point, we need larger scale training sets, right? So there are different types of thematic products available at continental, regional levels, and we would like to make jointly use of existing thematic products. And now we know that although these thematic products can provide us labels with zero annotation cost, they can be also noisy. Noisy means maybe some labels can be missing, maybe some labels can be wrongly annotated, and so on. So we need search and retrieval systems that are robust to label noise in the training. So this is actually currently what we are working on. And so I also would like to mention that the noise can also appear in the image captions. So if you are typing what you want to search for, there can be some typos, or the training set with image text pairs can have noisy correspondence also. So developing image search and retrieval systems that can be really targeting noise also in the captions, in the textual data, in addition to class labels assigned to the images, is very, very timely. Okay. So, and here, that is the end of my talk. I would like to just highlight that all the methodologies that I mentioned today, you can find the papers available in our group website, and also the software. For all the algorithms, we made publicly available all our codes. Please scan this QR code if you are interested in having access to our software. So then, yeah, thanks to European Research Council for supporting our research through the BigEarth project. Yeah, thank you very much. And now I am looking forward to answering your questions.
Thank you so much, Begum. I believe that we have learned so much, and we have a lot to study and to read your papers, also to deepen more into what you presented, because obviously it's not an easy topic. Definitely, we are in the state of art of machine learning applied to Earth observation. This is not only the today research, is also the future research, as a matter of fact. And thank you also for giving us the last recommendation with respect to what are the most important topics to focus. And I agree completely also with respect to the problem of the robust, doing something in a robust way. I believe that it's one of the main problem, because very, very often we get some results, but we don't know how good are those results, as a matter of fact.
Yeah, exactly.
Yeah, but I have some questions for you.
Okay, perfect.
Yes, so the first point is this one, because so you are using Corinne 2018 for labeling the Sentinel 1 and 2 that, as a matter of fact, have higher resolution. So my first question to you is, as now we are in the situation where the new high resolution land cover are appearing. So no more 100-meter resolution, something like that, but 10-meter resolution. Do you think that this will improve, and how much will improve this search?
Yeah, so actually, I guess you are referring to ESA's land cover map, right?
Yes, yes.
Okay. So this is an excellent input for us. Yeah, so we are very much interested in also for our Sentinel-2 pitches, mapping the labels provided by this ESA's land cover map. So yeah, I believe that that is the right direction. So at the time while we were developing BigEarthNet, such data was not existing. So very recently it became publicly available, and yeah, we are very excited for that, and we think that it can, because it can provide actually much more reliable labels to us. Korean labels are also sometimes complex to be represented in Sentinel-1 and Sentinel-2. So yeah, so
yes,
we are very positive.
The only point I'm asking to myself is if they are not too detailed, so too many, because now you have a certain number of labels, but if you consider higher resolution, obviously the number of labels is increasing, and therefore also in terms of search, probably it's more difficult to deal with it. But yes, I have the impression, for sure, the feeling that it will improve, but I have no idea about how much it will improve. And I don't know if you have the feeling about that.
Actually, it will, I mean, so at the end, it can increase the reliability of the machine learning models. So because we are training the models by using this data set, right? So if you have images and much more reliable labels assigned to images, the machine learning models trained by using this data will be much more reliable. So that's why I think that reliability of the models can be improved by using such labels.
Yeah. And then again, something related to the annotation. Have you considered also using, because I know that the quality of this data set in Europe is enough good, have you considered using OpenStreetMap?
Exactly, yes. So we are, I mean, for BigEarthNet, we didn't use OpenStreetMap tags, but we are working in different projects with OpenStreetMap tags. So it's, but there we can also see that some tags are missing, some tags are wrongly there. Maybe there is a land cover change happened after the tag is assigned. So that's why also for that. So it's very important to work towards developing machine learning models that can learn noise in the labels during training. And we have a project funded by German Research Foundation, and there we have a small data set, Sentinel-2, annotated by OSM text, and there we are working on label noise robust model development, for example. Yeah, so for volunteer geographic information in general, I can tell that that's a very relevant input for machine learning, right? But we just need to learn how to make good use of it.
Yeah, and then obviously the accuracy is very variable. Consider different parts of the world. We did some work about accuracy of, for instance, buildings. We consider Lombardy, which is the region where I live, and what we saw is that both referring to the accuracy, spatial accuracy and completeness is very good. As cartographer, we can say that is comparable to a map of scale 1/5000. That is very good as a matter.
Yeah.
But obviously, we can say this in this region. We don't know in general. We know that in Europe is enough good, but not everywhere, obviously. And so we have still this problem of dealing with respect to robust. We need to have some robust algorithm able of better understanding if there are mistakes, if something is missing, and so on.
Exactly.
With respect to OpenStreetMap, I have again another question, because are you using both, how to say, the map as it is one band, an image with only one band, and the tags for the annotation, or are you using only the annotation?
Okay, so we are using images with all the bands existing.
Yeah.
So, for example, in Sentinel-2, all the bands of Sentinel-2, or just the bands with 10 meter and 20 meter resolution. So, depending on the application that we have in our hands.
No, but I'm thinking about OpenStreetMap. We were speaking about OpenStreetMap.
Yeah. So,
you have the drawing, as a matter of fact, the map.
Yeah. Yeah.
The drawing of the map and the tags. The tags can be the annotation, but besides the annotation is telling you which elements are there, but not where they are. But if you consider the drawing of the map of OpenStreetMap, you have also the location where the different elements are.
Yeah, yeah.
So you have this double.
Okay. So if the application in our hands is image search and retrieval, for training, it is it's enough to have, depending on the model, the machine learning model that we will be using, but in most of the cases, it is enough to have images and OSM text assigned to images without specific coordinates. So like if you have a patch of, let's say, 1 kilometer by 1 kilometer area, we just assign the labels to this area, saying that in that patch, there is this classes. So, and we teach the model to learn this, to represent this in the model.
Okay, so you don't refer to the topology, as a matter of fact, to the distribution of the different objects inside the piece of Earth that we are considered for training the model.
If you like to use this graph-based approach, for example, that I introduced, there you may need the pixel-based labels. So there, it's not enough to have the labels assigned to the patch itself, but because if you would like to model the regions and region relations, we need pixel-based tags.
Yeah.
But also, I mean, if the problem is semantic segmentation for long cover maps generation, we need pixel-based labels in any case, right? So, yeah, depends on which model we will be using and which is the final task in our hand.
Yeah. Okay, then I have another question, my last question, and to better understand and also help the floor better understanding. Suppose, for instance, that there is I make one example, then I will make another one. Suppose that there is one class that is not so common, so it is underrepresented at the global level. For instance, wetlands. So part of the world where there are wetlands, also in Europe, with your method of searching, we can select the examples and we can query about the places in Europe where there are wetlands.
Exactly.
Correct?
Exactly. So that's a very good idea, actually. So on the one side, we always, I mean, it's very common to have training sets with class imbalance problems. So we have some image patches with rare classes, right? So during the training, this can create also a problem because the model may not learn perfectly that class if that is a minority class. And one of the approach to handle this is to, of course, to increase the number of patches including that class, right? And this can be addressed by using a search and retrieval algorithm because we can select a query that includes that class to retrieve images including that class, and we can just take it and include it in our training set.
Yes,
that's a good idea.
And then if you want, you can also validate them just to be sure, or part of them like is done generally for validation of data set. So
exactly.
And that is the first, but a second example can be, for instance, if there is a disaster and there are buildings that are destroyed. So it's also possible to make a query like this one, show me all the parts of the world where there are buildings, destroyed buildings.
This is actually one of our goals for the near future, because this is very interesting to search databases, archives for a specific change information. And so far it was challenging because of the lack of training data sets that model different types of change. Because at the end, we need an annotated data set of, for example, in this case, pairs of images with collapsed buildings and not. Right, so that the model can learn to characterize this, to search and retrieve that. That was our challenge, to have this data set. But now what we see that very recently some change detection data sets made publicly available, and they are at very large scale, and they can be easily converted to a change retrieval problem. And that can allow us to have a training set for change retrieval, train it, and so on. So that is a very, very interesting research direction, and we are now very close to research on it because of some new data availabilities.
Fantastic. Yes,
Yeah.
yes, I believe that these application that you made, or the system, because it's not simply an application, can be very useful, at least for these two cases. I agree completely with you. But then I have another question.
Okay.
So this other question is that this system is working well with Sentinel-2, Sentinel-1 data that are more or less these kind of similar resolution. Let's say it's not the same, but similar. But what happens if we take, for instance, higher resolution images, or no, let us say higher resolution images? This is the first question. And my second question is, because we already have some hyperspectral satellite now, and we are going toward having also some more hyperspectral. So is your system suitable also in these cases? I believe yes, but I want to have an answer for you. And in your opinion, both the two cases, higher resolution and hyperspectral, can add just a bit or can add a lot in this system? Yeah.
Yeah, that's a very, very good question as well. It is in our tables, I mean, in our agenda, and we are discussing about that a lot with our researchers at my team. So the answer is yes, but under some conditions. So it's, of course, we are very much interested in providing pre-trained models on BigEarthNet, and the models are different models that I shortly mentioned today, for example. But then if you would like to apply our models to another data set with slightly different characteristics, a research on domain adaptation, domain generalization is needed, according to me, because sample distribution will change, and the models cannot be directly cannot be generalized directly to a Naive domain. Okay, so Naive domain can be a very high resolution data or hyperspectral data and so on. So how to adapt a model trained on BigEarthNet to another data set? I think the answer should be based on domain adaptation, domain generalization, and so on. So that's a very good research direction as well. So of course, there are different challenges. If you are talking about hyperspectral, the number of bands is significantly higher than what we have in Sentinel-2. So the model should be adapted accordingly. And plus the spatial resolution differences, right? Like in Sentinel-2, we have 10 meter, 20 meter resolutions. and maybe in hyperspectral 30 meter. So it's slightly different. It can generalize well, but we need to research how to generalize better. Okay, considering special spectral characteristics. So I think that's a good research direction.
Yeah, so the interesting point of this talk with you, thank you again, is that we focus on something which is the state of art in this domain, but we are giving also good ideas to young researchers. I'm pretty sure that there are many young researchers here listening to you. And the relevant point is that is plenty of research questions that we have to solve. So that is very challenging, but very exciting. It means that there is a lot to do. So I did a lot. You are doing so well, but to the young researchers here, be sure that you will have a lot of things to do for the future, because there are so many open directions in researching in this field. Then I don't know, I will leave you the last word, Begum, if you want to say something, and then we can close.
Okay, so thank you very much for joining us and listening us. So I hope you enjoyed the talk. We are in our team, we are strongly supporting open science, and as I mentioned before, all our software is publicly available. If you are interested in that in this field, please have a try, and if you have any open issues, feel free to contact me and I will be happy to help and support. And all the best with your works.
Thank you so much, and to all people here, thank you for attending, and see you next time. Bye-bye.
Bye-bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.